Hello everyone, my name is Yunpeng. I'm introducing our ICSE paper to you. And the paper is named Static Inference meets Deep Learning, a hybrid type inference approach for Python. The co-authors of this paper are 翠云高, 宗杰李, 博维高, David Law, 启润章, and Michael Liu. In this video, I will talk about four major parts to you. Firstly, I will introduce some background knowledge and our motivations. Then I will talk about our approach in detail. In the third part, I will briefly describe the major evaluation results, and in the last part, I will give some open resources for further research. So the first part is the introduction and the motivation. Seeing the title of our paper, you may have such a question. Why do we need to infer types for Python programs, as Python itself is naturally designed as a dynamically typed programming language? In these slides, I show a developer survey conducted by JetBrains and the Python Software Foundation in 2020. And there is a question in the survey asking about the most desired features that developers want to add in Python. The result of this question is surprising, as almost 20% of developers want the feature of static typing, or at least some strict type hinting. This result reflects the emerging needs of Python type inference. To fulfill the needs, there are some tools and approaches proposed. In this video, I classify them into two major categories. The first is static inference techniques, in which Pyre is a representative. Static inference techniques are usually rule-based and have very high accuracy. However, they suffer from the coverage problems brought by the dynamic features or some external calls in code. The other category are deep learning techniques. These techniques are usually data-driven and feature-agnostic, so they are free from the influence of dynamic features and they are very effective on common types. However, they cannot guarantee the correctness of their predictions and usually obtain low accuracy on real types. Given the comparison between these two major approaches, our insight is that can we just make use of the advantages of both approaches and then build a tool that can improve the coverage while maintaining the precision? We take an example to verify our insight. In the left of this slide, there is a code of a function named parse, extracted from an open source project. Our goal is to infer the types for the argument text and the return value. The right lists the ground truth types and results from some baseline approaches. First, we can see that the ground truth type of the return value is very complicated, as it is a tuple containing a list and a dict. For the static inference tools such as Pythona2 and PyType, they cannot infer the types of the argument text because it is at the beginning of the data flow and there are insufficient constraints to solve its type. But they are generally effective for the inference of the return value because they can successfully infer the most part of the return value. For the deep learning models such as typulars, they can successfully predict the type for the argument text, as the name text delivers strong type hints for the models. However, they cannot well handle the type for the return values, since the ground truth type may not even exist in the training set, so that the model can only find some similar ones as predictions. Meanwhile, the models cannot check whether the predictions are valid, as in the table we can see that typulars returns a type ordered dict that is never imported in current code. By combining both static inference and deep learning models, HiTyper first runs the static inference and infers the partial type of the return value. Then it identifies that the argument text hinders the inference of other variables, so it seeks deep learning models for recommendations. Under this case, typers can successfully give the type of the argument. So HiTyper directly uses this recommendation to complete the inference of the rest variables. This example verifies our insight that making use of the advantages of both static inference and deep learning can improve the performance of type inference. In the next part, I will introduce our approach in detail. Before talking about the specific designs, we first define the scope of types that we focus on in this paper. In this slide, we divide all types into two categories, built-in types and user-defined types. And we also give the formal definitions of them in this slide. Other work may also refer types as common types or real types according to the occurrence frequency in the dataset. Here we also find that the most common types are built-in types and the most real types are user-defined types. But as static inference is data insensitive, we keep using the formal definitions in this video. This slide shows the overview of our approach. Since we want to combine both static inference and deep learning, we need to bridge the communication between them. Therefore, we design a novel graph representation named type dependency graph given the input code. The type dependency graph indicates the type dependencies between variables in code, and there are some empty nodes in it, while our goal is to fill the empty nodes with types. So the first part of our approach is the type dependency graph generation. This part generates empty type dependency graph for static inference and deep learning models to infer types. Given the empty type dependency graph, HiTyper first conducts a forward type inference process on it and handle the variables that can be statically inferred. There are two possible results after conducting the forward type inference process. The first is that all variables can be statically inferred, and then HiTyper can directly output the result. But due to the dynamic features, it is more likely that HiTyper can only get a partially inferred type dependency graph from this process. So it needs the help of the deep learning models. Before feeding the partially inferred type dependency graph to deep learning models, HiTyper identifies the hot type slots. Here we refer hot type slots as the most important variables in the type dependency graph. Given these hot type slots, HiTyper passes them for the deep learning models to predict the types. This is to reduce the wrong types that may be introduced by the deep learning models. Since HiTyper is independent of deep learning models, here we do not talk about the details about how deep learning models predict types. So suppose HiTyper gets recommendations from the deep learning models. It then conducts a similarity-based type correction algorithm to map the never imported types predicted by the deep learning models into valid types in the current code. Next, HiTyper passes the recommended type dependency graph back to the static inference part. Now, not only forward type inference is activated to infer the types for the rest variables, but also backward type rejection is activated to filter out the wrong predictions from the deep learning models. The interaction between the static inference and deep learning models may happen several times until the type dependency graph is fully inferred. In the following slides, I will talk about the details of type dependency graph, static inference, and recommendations from deep learning models. First is the type dependency graph. We define type dependency graph as a graph with a node set and an edge set. There are four kinds of nodes. The first is symbol nodes or type slots that indicate the variables we need to infer the types. The second are the expression nodes that indicate the expressions producing new types in code. The last two are the branch nodes and merge nodes that are designed to handle the data flow branches and merges. In the type dependency graph, an edge from a node A to a node B indicates that the type of the node A is a precondition if we want to solve the type of the node B. The most important part of the type dependency graph is expression nodes, as they producing new types. Here in this slide, I show all expressions that may occur in the Python code. For each expression in the slides, we design some specific rules for it in the static inference process. And the basic format of a rule is as right. This format means that the expression E should have the type delta under the context pi. We also give an example of the rule we used for the expression L shift and R shift in the paper. In this rule, the things above the line are called preconditions, which we must know before activating this rule. And the things under the line are called conclusions, which indicate the result after we activate this rule. Among the conclusions, the part in the blue box is called typing rules in our paper. It infers the result type of the expression L shift and R shift produce. The part in the red box is called type rejection rules, as it verifies and rejects valid types for operands. Generally, we do not need type rejection rule in static inference process, as static inference can be proven sound. But HiTyper needs to handle the predictions from the deep learning models, so we specially designed the type rejection rules for each expression. The static inference part of HiTyper is built upon the typing rules and type rejection rules. As we have the type dependency graph and the expression nodes with rules in it, now we can just reformulate the static inference process into a graph traverse process. For the forward type inference, HiTyper starts from the nodes without input nodes and forward traverses the type dependency graph. In this process, typing rules are activated to infer the result types. For the backward type rejection, HiTyper starts from the nodes without output nodes and backward traverses the type dependency graph. In this process, type rejection rules are activated to reject the operand types. After the static inference process completes, if the type dependency graph is not fully inferred, then HiTyper identifies the hot type slots in it. The insight of hot type slot identification is that among all blank type slots, some key type slots hinders static inference from inferring other slots. So we can just let the deep learning models to predict the types for these key type slots to reduce the wrong predictions from deep learning models. To achieve this goal, HiTyper first obtains a subgraph of type dependency graph that contains all blank type slots. Then it employs a dominator identification algorithm to find the domination relationship in the type dependency graph. Based on the domination relationships, HiTyper gradually removes type slots that are fully dominated by other type slots, because this means that these type slots can be inferred by static inference once other slots are predicted. By iteratively conducting this process, HiTyper finally gets the smallest subset of blank type slots, and these subsets are hot type slots that should be passed to deep learning models for predictions. Given the predictions from deep learning models, HiTyper also implements a similarity-based type correction algorithm to map the never imported types into a valid type. For example, deep learning model may give a prediction torch.tensor, but this type is never imported in current code. Instead, TensorFlow.tensor is imported. Under this case, HiTyper maps torch.tensor to TensorFlow.tensor based on the similarity-based type correction algorithm. The algorithm is based on two similarities. The first is the type name similarity, which is calculated between predicted types and all valid types. The second similarity is variable name similarity, which is calculated between variable names and all valid types. We add the variable name similarity in this algorithm because we find that in many cases, variable names gives very strong hints to predict the correct types. So these are the basic methodology of our approach. In the next part, I will briefly discuss the major evaluation result. In the evaluation process, we mainly focus on 3 research questions. The first is, how effective is high-typer compared to baseline approaches? The second is, can high-typer well predict the real types? The last is, what's the performance of the static type inference component in high-typer? In the evaluation process, we choose 3 kinds of baselines. The first baseline is a naive baseline that represents the basic performance of data-driven method. And the second kind are 2 static inference tools named PyType and PyReinfer. The last kind are 2 state-of-the-art deep learning models named Typulars and Type4Py. For the dataset, we directly adopt the dataset from Typulars and Type4Py. We also list some statistics of our test set in the table in the slides. For the matrices, we adopt the matrices used in Typulars and Type4Py. The first metric is exact match, that requires the result to exactly match the human annotations. The second metric, match to parametric, is a bit more loose. It only requires the outermost type of the result to match the outermost type of the human annotations. So the table in this slide shows the overall performance of high-typer and some baseline models. We show the top 1, 3, and 5 result in this table. From the table, we can see that high-typer outperforms all baselines in both datasets under different type categories. And it also shows 11 to 50% improvement on overall type inference, while the most significant improvement is on the inference for return values, in which high-typer shows an improvement of 20 to 40%. The table in this slide lists the performance of high-typer and some baseline deep learning models on real types and user-defined types. As we talked in previous slides, data-driven method can hardly handle real types. So we can see that the performance of the naive baseline is almost 0 under this case. Also, the performance of Typulars and Type4Py are quite low. However, high-typer greatly alleviates the prediction issue of real types faced by the deep learning models by achieving a more than 30% boost. This is taking the advantage of the static type inference component. The table in this slide shows the performance of the static inference component of high-typer and other baseline static inference tools. Here we add a new metric, which is the number of correct annotations to reflect the coverage of the static inference approaches. From the table, we can see that high-typer obtains the most correct annotations and also has higher accuracy in most cases. This means that only considering the static inference part, high-typer still outperforms current static type inference tools by inferring 2 or 3 times more variables with higher accuracy. So this is the basic evaluation result. In the last part, I will introduce some resources that you can access after listening to this video. For the preprint of our paper, you can access it on arXiv through this link. And if you want to access the code of our tool or some dataset and the more detailed evaluation result, you can get them on our GitHub through this link. And if you have any questions regarding this work, please feel free to contact this email address. And this is the end of the video. Thanks for your interest.